Less than 24 hours ago, this channel told you about a buried fault beneath the middle of America that almost nobody knows the name of. A fault that, in 1812, made the Mississippi River flow backwards. We told you it had gone quiet. We told you scientists couldn't agree whether it was dying, sleeping, or quietly reloading. We published the video. We went to bed. And this morning, the Earth fact-checked us in real time. A magnitude 4.0 earthquake ruptured inside the core of the new Madrid Seismic Zone, felt across 5 states, the biggest event this fault has produced in 5 years. And on the same calendar day, the Sun fired 2 X-class solar flares and launched a coronal mass ejection directly at Earth, while an earthquake swarm erupted off the coast of Crete. 3 systems, 1 24-hour window. Stay with me, because this story stops being a coincidence and starts feeling like something else entirely. And by the time we're done, you'll understand why some of the world's leading geologists are quietly, genuinely worried that the fault that reversed the Mississippi in 1812 may have just started reloading. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe, because this story has an active observation window and we are not leaving it. Drop a comment, tell me where you are watching from. And tell me this, a fault in the middle of America just fired its biggest quake in 5 years. The Sun launched a coronal mass ejection straight at Earth, and the seafloor off Crete started shaking at the same time. 3 systems, 1 day. Coincidence, or something we are not ready to call? Tell me what you think. Now let's get into this. Part 1. The 24-hour whiplash. There is a particular kind of professional whiplash that only happens in this line of work. You spend weeks researching a story, you read the papers, you pull the data sets, you interview the sources, you record the video, you publish it, you go to bed, and then you wake up and the Earth has, without consulting you, decided to fact-check your script in real time. That is roughly what happened this morning. We had spent the previous video walking you through the history of a fault system that sits beneath the middle of the United States, the new Madrid Seismic Zone, and we had made a fairly specific point. We said that one of the reasons this fault is so difficult to understand is that it has gone quiet for long stretches, with almost no meaningful seismic activity for years on end, and that this silence is exactly what makes some scientists nervous and other scientists confident. Silence on this fault is interpretive. It does not mean what silence usually means. And then, less than a day later, the fault broke its own silence with the largest earthquake it has produced in about 5 years. Let me give you the raw numbers first, because the numbers matter, and we're going to come back to them over and over across the next 2 hours. The event was initially logged by the United States Geological Survey as a magnitude 3.9. Within a few hours, that number was upgraded to a magnitude 4.0 after seismologists manually reviewed the waveform data coming in from regional stations. That upgrade might sound like a rounding detail, but I want you to sit with it for a second, because it tells you something about how this science actually works. When a quake happens, the initial magnitude is computed automatically by algorithms, using the first waves to arrive at the nearest stations. That automatic number is fast, but it is a first approximation. Human seismologists then look at the full waveform from multiple stations over the full duration of the shaking, and they refine the estimate. When they nudged this one from 3.9 to 4.0, they were telling us, in their quiet and understated way, that the energy release was slightly larger than the machine's first thought. The human eye saw something the algorithm undercounted. The epicenter of this quake sits inside the core of the new Madrid Seismic Zone, roughly north of Memphis, Tennessee, in a region that straddles the Mississippi River and crosses the borders of Tennessee, Missouri, Arkansas, and Kentucky. The depth was approximately 12 miles below the surface, which is what seismologists call mid-crustal depth. That is meaningful. 12 miles down is not a shallow event, and it is not a particularly deep one either. It is the kind of depth where the rock is warm, brittle in places, and under real stress. Now, here is what I want you to understand about the felt radius. This quake was reported as being felt across at least 5 states, with shaking perceived out to a radius of roughly 200 miles from the epicenter. For a magnitude 4, that is an enormous footprint. If you had dropped this exact same quake, same depth, same energy on the San Andreas Fault in California, the felt radius would have been a tiny fraction of what we saw today. People in the next town over might have noticed. People 100 miles away almost certainly would not. But here, in the middle of the continent, people in Illinois felt it. People in northern Mississippi felt it. People in parts of Indiana reported weak shaking. The quake essentially broadcast itself across the Midwest. No damage was reported, no injuries, no buildings came down, no bridges closed. By every standard measure that emergency managers use to rank an earthquake's significance, this was a non-event. And yet, the perception footprint was enormous. Thousands of people logged felt reports with the USGS within the first hour. That gap between the physical footprint and the perception footprint is exactly the thing we're going to return to again and again tonight, because it is the signature characteristic of this fault, and it is central to understanding why geologists are looking at this small quake with something closer to unease than reassurance. To understand just how unusual today's event is, you have to look at what the zone has been doing for the 30 days leading up to it. In the month before this quake, the new Madrid Seismic Zone produced roughly 25 small earthquakes. The largest of them was a magnitude 2.3, the rest were smaller. Most were so small that no human anywhere felt them. They were instrumental events, picked up only by seismometers, recorded on the network, logged, catalogued, and essentially ignored. And then this morning, out of that baseline of barely there microquakes, the zone produced an event that was roughly 500 times more energetic than the background maximum. I want to slow down on that 500 number, because earthquake magnitude is not intuitive. It is a logarithmic scale. Each whole number increase in magnitude represents roughly 32 times more energy released. So going from a magnitude 2 to a magnitude 3 is about 32 times more energy. Going from a magnitude 2 to a magnitude 4 is roughly 32 times 32, which is about 1,000 times more energy. Going from a 2.3, which was the largest event in the last 30 days, to a 4.0 is an energy jump of approximately 500-fold. That is the jump that happened today, in the same geological region, inside the same fault system. In the language of the Earth, that is not a gradual increase. That is the system going from a whisper to a shout. And this is where I have to be careful, because a magnitude 4 is, by global standards, a small earthquake. Somewhere on Earth, right now, a magnitude 4 is probably happening. They are common. They are unremarkable. In California, in Japan, in Indonesia, a magnitude 4 barely registers as news. If you live along a plate boundary, you have probably slept through several of them. But here is the thing. It is not the size of this quake that has people looking twice. It is the context. It is the pattern. It is the silence that came before it. And it is the fault that produced it. A magnitude 4 on the San Andreas is background noise. A magnitude 4 on the New Madrid, after a month of microactivity, inside a fault system that once produced the largest earthquake sequence in the recorded history of the eastern United States, is something else. It is what seismologists sometimes quietly call a pattern rupture. Not a rupture of the Earth exactly, a rupture of the pattern, a small break in the expected behaviour of a system that we already do not fully understand. This is not a big earthquake, but it is, in every way that matters for this story, a strange one. And that is the question we're going to spend the next 2 hours circling. Because if a quiet fault suddenly starts speaking, you have to decide whether what it is saying is meaningless or meaningful. You have to decide whether the silence that came before it was rest, or whether the silence was loading. And that is a question that, as you are about to see, has divided the world's leading seismologists for decades, with no resolution in sight and no easy answer for the millions of people who live on top of this fault and have no idea it is there. Part 2, the pattern break, nobody watches for. The reason this particular magnitude 4 matters is not because it was big. It is because it arrived in a sentence that, up until this morning, read as background silence. And to understand why that sentence changed today, you have to understand the handwriting of this fault. In a normal month, the New Madrid Seismic Zone produces somewhere around 15 to 20 small earthquakes. Over the course of a year, that number climbs to roughly 200. Most of these events are very small, below magnitude 2.5, which means almost none of them are felt by anyone. They show up as little wiggles on a seismometer, get catalogued, and disappear into the data stream. This is the baseline. This is what the fault sounds like when it's doing nothing in particular. This is the noise floor. For the last 30 days, the zone had actually been operating slightly below that noise floor, 25 small events in a month is on the lower end of what seismologists consider normal activity. And the largest of those events, the one that stood at the top of the 30-day list, was a magnitude 2.3. To put that in perspective, a 2.3 is roughly the amount of energy released when a medium-sized tree falls in a forest. It is barely detectable as an earthquake. It is not felt. It is not reported in the news. It is simply counted and filed away. So the month leading up to today looked, from the outside, like a quiet period. If you were a casual observer, you would have said the fault was napping. If you were a sensationalist, you might have said the fault was overdue. If you were a cautious seismologist, you would have said that the zone was exhibiting typical background behaviour, with no clear trend either up or down. Here is where it gets a little more interesting. Earlier on the same day as the magnitude 4 event, in the very early morning hours, there was a smaller foreshock, a magnitude 1.8 event, also inside the new Madrid zone, roughly in the same area. A 1.8 is tiny. Almost no one would have felt it. It barely rises above the noise floor. Under most circumstances, it would not even register as worth mentioning. But in hindsight, with a magnitude 4 event arriving later in the same 24-hour window, in the same geographic area, that small 1.8 takes on a slightly different character. It becomes, arguably, a foreshock. Or at least, it becomes something that looks like a foreshock if you're willing to squint at the data. I want to be very careful with this word, foreshock, because it is a word that seismologists use with a lot of caution, and you should too. A foreshock, strictly speaking, is a smaller earthquake that occurs before a larger earthquake in the same fault system, and that is only identifiable as a foreshock in retrospect. That is the key. You cannot know that a quake is a foreshock in real time. You can only know it after the larger event arrives. Before that, a 1.8 looks like a 1.8. It looks like background, it looks like nothing. You only earn the label foreshock if the Earth decides, later, to make the pattern mean something. So the 1.8 this morning might be a foreshock to the 4.0. Or, more likely, the 4.0 is simply the largest event in a small cluster, and the 1.8 was a precursor micro-event that happened to share its neighbourhood. Both interpretations are reasonable. Both are unprovable in the short term. This is how the science has to work. You collect the data, you describe what you see, and you resist the temptation to tell a story until the Earth gives you enough material to justify one. That said, a magnitude 4 is not historically unprecedented here. It is important to say that out loud. In 2011, the zone produced a magnitude 4.7. In 2021, it produced a magnitude 4.2. Both of those were larger than what we saw today. So in terms of pure magnitude, today's event is not a record breaker. What makes today unusual is not the size. It is the timing. It is the cluster context. It is the fact that it arrived after a particularly quiet stretch, and that the energy jump from the 30-day maximum to today's event was so steep. This is what I mean when I talk about a pattern rupture. The fault did not produce a bigger quake than it has produced before. It produced a quake that broke the recent pattern of near silence in a way that, statistically, stands out. And in a fault system as poorly understood as this one, statistical standouts are worth paying attention to, even if we cannot yet say what they mean. Here is the core tension. In seismology, there is a concept that you could describe as short-term seismic silence followed by release. The idea is that sometimes a fault zone goes unusually quiet for a period before producing a larger event. The reasoning is that in the final stages of stress accumulation, the fault may temporarily lock up, suppressing the small background quakes that normally bleed off minor stress, until that locked section finally slips in a larger release. This is a real phenomenon that has been observed in some fault systems. But, and this is very important, it is not a reliable predictor. Many quiet periods are followed by nothing. Many large earthquakes are not preceded by quiet periods. The pattern exists. It is just not predictive enough to be useful in any real-time forecasting sense. So when we look at today's event, with its 30-day quiet period and its sharp energy jump, we are looking at a pattern that could, in a small percentage of cases, precede something larger, or it could be nothing. It could be exactly what a fault of this type does when it is simply releasing accumulated minor stress in a slightly lumpy rhythm. Both are plausible. This is the first crack in the wall of the simple explanation. The simple explanation would be that everything that happened today was normal background activity, and we should go about our business. But as we dig into the details, the word normal starts to do a lot of work. Normal compared to what? Compared to the last 30 days, this is abnormal. Compared to the last decade, it is within the range of events we have seen. Compared to the last 200 years, it is a whisper in a system that has screamed at least 3 times in recorded history. Depending on which timescale you choose, this quake is either background noise or a data point that deserves a second look, and that is the first signal, the first faint indication that the story we thought we understood about this fault might need to be updated. Not rewritten, not panicked over, just carefully, quietly, rigorously reconsidered. Because a quiet fault suddenly speaking is the exact kind of thing that the scientists who study this zone have been waiting to see. And whether what it said today was meaningful or not, it said something. So what do you do with a data point that could mean everything or nothing? You widen the frame. You look at what else was happening on the planet at the same moment, and when you do that, the picture gets more complicated, not less. Part 3. The same-day convergence. Here is where the story starts to bend. Within the same 24 to 36-hour window in which the New Madrid earthquake happened, 3 other significant events occurred across the Earth system. Each one, on its own, would have been worth a short news segment. Together, on the same calendar day, they form a cluster that anyone with a pattern-recognizing brain would notice. The first of these was happening 93 million miles away, on the surface of the Sun. An active region on the Sun, catalogued as Active Region 4419, produced 2 X-class solar flares within a 7-hour window. X-class is the highest category of solar flare on the standard classification system. These are the largest, most energetic flares the Sun produces. Associated with the second of those flares was a coronal mass ejection, a massive expulsion of magnetized plasma from the Sun's corona, and early trajectory modelling indicated that the ejection was Earth-directed. Not a glancing blow, not a near miss, a direct path, arriving in a window of a few days after the flare itself. The second event was on the other side of the Atlantic in the eastern Mediterranean. Off the southern coast of Crete, an earthquake swarm broke out, with the largest event measuring magnitude 5.8. A swarm, in seismological language, is a cluster of earthquakes of similar size that occur in the same area over a short period, without a single clearly dominant main shock. The Crete swarm is in a very different geological setting from the New Madrid zone, which we will get into later, but the timing was striking. The third layer is the background noise of global seismicity. On the same day, moderate earthquakes were recorded in Kamchatka, in the Aleutian Islands, in Alaska, and in several other active regions around the Pacific Rim. None of these were particularly large, none of them were historically significant. But they were clustered in time, in a way that, when viewed alongside the New Madrid event, made the entire 24-hour window feel like a period of global Earth activity. Now, I want to pause here and say something important, because this is the moment where this story becomes very easy to tell wrong. There is a temptation, a deep and very human temptation, to look at a cluster of events like this and conclude that something is connecting them, that the Sun and the Earth are talking to each other, that the Mediterranean swarm and the New Madrid quake are part of the same planetary process, that the coronal mass ejection and the fault rupture are linked by some unseen mechanism. This temptation is strong, and it is not irrational. Humans are pattern-recognizing animals. We survived as a species because our ancestors noticed that the rustle in the bushes and the lion in the clearing tended to come in that order. Pattern recognition is our superpower, and it is also, sometimes, our bug. Let me correct one thing right now, because I want to get it out of the way clearly and early. The 2 X-class solar flares today did not cause the New Madrid earthquake. I want to say that plainly, because I have already seen speculation online that they did, and the timing alone makes it impossible. The earthquake happened first, the flares happened afterward, or at least the relevant flare activity occurred later in the same calendar day. You cannot have an effect arriving before its cause. The coronal mass ejection associated with these flares has not even reached Earth yet, and will not reach Earth for another day or two. Whatever is going to happen to our magnetosphere when that ejection arrives has not happened. So any theory that connects the flares to the earthquake has to contend with the simple fact that the quake came first. That is the timeline. That is the constraint. So what we are left with for now is what scientists call temporal clustering. That is the phenomenon of multiple events occurring close together in time, without any established causal relationship between them. Temporal clustering is not proof of connection. It is a description of coincidence, and coincidences happen constantly. On any given day, you can find multiple earthquakes, multiple solar events, multiple weather anomalies, multiple geomagnetic disturbances. If you choose your 24-hour window carefully and list everything that happened inside it, you can almost always construct what looks like a pattern. And yet, that is not the end of the story. Because the question is not whether these events are causally connected. The question is why the New Madrid quake today felt louder in context than its magnitude would suggest on any other day. And the answer, I think, is exactly this convergence. When a quiet fault speaks, and on the same day the sun is screaming and the Mediterranean is rattling, the human mind assembles those three data points into a picture, and the picture looks like a system in motion. It is not. It probably is not. But the feeling is real. This is what I mean by the coupling illusion. When multiple unrelated systems show elevated activity within a short temporal window, we feel the coupling even when there is no physical coupling. And the feeling is not useless. The feeling is what drives us to look more carefully at each individual event. It is what drives us to ask whether the New Madrid quake, in isolation, deserves attention. Stripped of the solar flares, stripped of the Crete swarm, stripped of the global convergence, is today's magnitude 4 still notable? And the answer, I think, is yes. But not because of the flares, not because of Crete. It is notable because of the fault it came out of, because of the silence that preceded it, because of the history of that silence, and because of the scientific debate that has surrounded this particular piece of ground for the last 40 years. The convergence makes the quake feel louder, but the quake itself, in the context of its own home turf, is what actually matters. And that home turf, as we're about to see, is one of the strangest, most contested and most misunderstood pieces of geology on the North American continent. Part 4. Why this fault is different. Before we go any further, we need to talk about what kind of fault the New Madrid Seismic Zone actually is, because it does not behave the way most people think faults are supposed to behave. And if you do not understand that difference, then everything else we are about to discuss, including why scientists cannot agree on what today's quake means, will not quite click. When most people think of earthquake zones in the United States, they think of California. They think of the San Andreas. They think of plate boundaries. And that mental model is mostly correct for the West Coast, because the San Andreas and the faults around it sit exactly where two tectonic plates, the Pacific Plate and the North American Plate, are sliding past each other. You can see this on any geological map. You can trace the boundary, you can measure the slip rate with satellites. The mechanism is visible, observable, and relatively well understood. Plate boundary earthquakes happen for a reason you can point to on a map. The New Madrid Seismic Zone is not like that. It sits nowhere near a plate boundary. It is in the middle of the North American Plate, roughly 1,000 miles from the nearest tectonic edge. In the standard textbook picture of how earthquakes work, this zone should not be producing earthquakes at all. It should be a stable, quiet piece of continental interior, like most of the land between the Rocky Mountains and the Appalachians, and yet it produces earthquakes, lots of them. Small ones mostly, but occasionally, historically, some of the largest earthquakes ever recorded in the eastern half of the continent. This is what scientists call an intraplate fault system. Intra meaning inside, plate meaning the tectonic plate. A fault inside a plate rather than at its edge. And intraplate faults are, as a category, some of the strangest and least well understood features in all of seismology. To understand why, you have to understand the history of this particular piece of crust. About 550 million years ago, when the continents were arranged in a configuration nothing like what we see today, a long narrow valley tried to form across what is now the middle of North America. The crust was pulling apart. A rift was opening. If it had continued, it would have eventually split the continent into two pieces, with an ocean growing in between. But for reasons that are still debated among geologists, the rift stopped. It did not finish opening. It did not complete the continental breakup. It simply stalled, and then the crust around it stabilized, and the rift was buried under hundreds of millions of years of sediment. This is what is now called the Real-Foot Rift. It is a failed rift. It is the scar of a continent that almost split, and then didn't. And that scar, even though it is buried, even though it has been quiet for most of its existence, is still there. The crust above it is still weaker than the surrounding rock. The zones of fracture along its edges are still present. And when stress builds up in the middle of the North American plate, which it does, slowly from a combination of far-field tectonic forces and internal mass distribution effects, that stress finds the weakest path. And the weakest path is the old rift. So that is the basic setup. An ancient wound in the continent, 550 million years old, quietly concentrating stress that has to go somewhere. And every few hundred or thousand years, some of that stress releases, sometimes in small quakes, sometimes in very large ones. But there is a second thing that makes this fault system dangerous, and it has nothing to do with how the stress accumulates. It has to do with how the shaking travels once a quake happens. In California, when a magnitude 4 earthquake occurs, the seismic waves spread outward through the crust and the upper mantle, and as they travel they lose energy. They are absorbed, dampened and scattered by the fractured, heated, chemically altered rock that makes up a tectonically active region. Within 50 miles, most of the shaking is gone. Within 100 miles, it is almost imperceptible. The rock around the fault acts like a sponge. It soaks up the energy. The rock beneath the central and eastern United States does the opposite. It is old, cold, stable, dense, and mostly unbroken. When seismic waves travel through it, they lose very little energy. They can travel hundreds of miles without significantly attenuating. A magnitude 4 in the middle of the North American plate can be felt at distances where a magnitude 4 in California would be undetectable. The crust here does not absorb the shaking, it carries it. There is a metaphor I like for this, and I think it is worth slowing down on. Imagine the difference between dropping a hammer on a pile of wet sand versus dropping it on a giant bell. The wet sand absorbs the impact. You hear a thud, and it is local. The bell rings. The energy is not absorbed, it is transmitted, and the ringing carries far beyond the point of impact in every direction. The crust beneath the New Madrid Seismic Zone is, seismologically speaking, a bell. And today's magnitude 4 was a relatively small hammer, but the bell rang out to 200 miles. 5 states heard it. That is not because the hammer was unusually heavy. That is because the bell is unusually good at ringing. This is why small quakes in this region feel disproportionately large. This is why a 4 here broadcasts across the Midwest. And this is why, when scientists try to estimate the potential damage from a larger event in this zone, they use numbers that sound almost hallucinatory. Because if a 4 can be felt in 5 states, you have to start thinking very carefully about what a 6 or a 7 or a 7.5 would do. This fault can feel quiet and dangerous at the same time. That is the paradox we have to hold in our heads as we move forward. The quiet is real, the quiet is physical, the stress is not being visibly released, the surface is not deforming in ways our instruments can easily detect, but the crust underneath is wired for broadcast, and the ancient fracture zones that run through it are still there, still weak, still concentrating whatever stress does exist. The silence is not safety. The silence might, depending on which model you trust, be loading. And that brings us to the event, the single event, that anchors every conversation about this fault. The event that made the Mississippi River flow backwards. Part 5. 1811 and 1812, the benchmark event. To understand why a magnitude 4 today matters, you have to understand what happened in the winter of 1811 and the spring of 1812. Because that is the event that set the upper bound of what this fault system is capable of, and it is the event that every current estimate of hazard is, in one way or another, measured against. Between December of 1811 and February of 1812, the New Madrid Seismic Zone produced not 1 but 3 massive earthquakes, spaced roughly over a 2-month window, with hundreds of smaller aftershocks interspersed throughout. The 3 main shocks are estimated in modern magnitude scales to have fallen somewhere in the range of 7.3 to 7.8. That estimate is approximate, because of course no one had seismometers in the American frontier in 1811. The magnitudes are inferred from historical accounts, geological evidence, and modelling of how the shaking propagated based on where damage was reported. The felt area of those earthquakes is where the numbers start to sound almost absurd. The shaking from the largest of the 3 events was felt across approximately 2.5 million square miles. Let me repeat that. 2.5 million square miles. Church bells rang in Boston, roughly 1,000 miles from the epicenter. In Washington, D.C., plaster fell from walls. In Charleston, South Carolina, people reported shaking. Residents as far away as Canada and the Gulf Coast described feeling the ground move. For comparison, the 1906 San Francisco earthquake, one of the most famous earthquakes in American history, had a felt area of roughly 375,000 square miles. The largest 1811 to 1812 event may have been felt over an area roughly 6 to 7 times larger. This was not because the 1811 earthquakes were necessarily larger in magnitude than 1906. In terms of raw energy, they may have been comparable. It was because of the crust, because of the bell. The central and eastern United States broadcast seismic energy in a way that the western United States simply does not, and that broadcast capability turned 1811 into a continental scale event. Near the epicenters themselves, the effects were almost beyond description. The ground deformed. Some areas sank, others rose, whole patches of forest tilted and fell. Sand blew up through the soil in geyser-like vents, driven by the violent pressurization of water-saturated sediments below. These features, called sand blows, are still visible today if you know where to look, and they are a critical piece of evidence for something we're going to come back to later. And then there is the story of the Mississippi River. You have probably heard it told as folklore or half-legend, but it is real. During the largest of the earthquakes, the riverbed itself was disrupted. The ground beneath the river warped. In some places the riverbed rose, in others it sank. Waterfalls briefly appeared where no waterfall should have been, and for a short period, in at least one location, the river appeared to flow backward. Not in the sense of the entire Mississippi reversing its course permanently, that did not happen, but in the sense that a large section of the river, temporarily, had its flow direction reversed by the disruption of the riverbed. Water was pushed upstream. Boats that had been floating downstream suddenly found themselves being carried in the wrong direction. Witnesses described the surface of the water boiling, cracking, and violently oscillating. One of the lasting physical scars from that sequence is Reelfoot Lake in northwestern Tennessee. Before the earthquakes, that area was forested floodplain. During the quakes, the ground subsided, the Mississippi briefly flowed into the depression, and when things settled, there was a new lake where no lake had existed before. You can visit it today. The drowned trees that used to be a forest still stand in the shallow water, stripped of bark and life, as markers of what happened there. So this is the event that anchors the hazard conversation. 3 massive earthquakes in 2 months, continental scale shaking, permanent reshaping of the landscape, a river that briefly reversed, a new lake formed, all from a fault that today produced a magnitude 4 and was felt, faintly, across 5 states. When you hold today's event up against 1811, the scale difference is almost comical. A 4 is not a 7. The energy difference between a magnitude 4 and a magnitude 7 is roughly a factor of 30,000. Today's quake is not a repeat. It is not even close. It is a faint echo inside a system that, when it fully speaks at continental volume. But that is precisely why today matters. Because the question is not whether today's quake is an 1811 event. It is not. The question is whether this quake, in the context of everything else we know about the fault, is a small sign that the system is still alive in ways our most optimistic models would like to deny. That is what the scientists who monitor this fault are wrestling with, and to understand why their answers disagree so violently, we have to talk about the one piece of the puzzle that nobody has solved. Part 6. The Reelfoot Rift Problem. Here is where the story stops being simple history and becomes an actively contested piece of science. We already established that beneath the New Madrid Seismic Zone, there is a buried failed rift system called the Reelfoot Rift. We established that it is about 550 million years old, and that it represents an ancient attempt by the continent to tear itself apart that ultimately failed and was buried under later sediment. And we established that even though the rift is buried, the fractures and zones of mechanical weakness associated with it are still there. The question that nobody can fully answer is this: is that failed rift currently accumulating stress, or has it released most of its stored stress and entered a quieter phase? This is not an academic question. The answer determines whether the New Madrid Seismic Zone is one of the most dangerous places in North America, or merely a mildly elevated hazard zone that is unlikely to produce a large event in any foreseeable timeframe. Billions of dollars of infrastructure planning, insurance pricing, and emergency preparedness decisions hinge on which answer is correct. and the scientific community genuinely does not agree. Here is why the question is so hard. When you want to measure whether a fault is accumulating stress, the most direct way is to measure strain at the surface using GPS stations. You set up a network of very precise GPS receivers across the region, and you watch, over years, whether the ground is slowly deforming. If a fault is locked and accumulating stress, the rock on either side of it is being slowly bent, and that bending shows up as very small but measurable movement in the GPS network. On the San Andreas, the GPS network shows clear, consistent, measurable strain accumulation. The Pacific plate is moving past the North American plate at roughly 1.5 inches per year. You can measure it, it is there. On the new Madrid Seismic Zone, the GPS network shows almost nothing. The measurements are at or below the level of detection for conventional geodesy. The ground is not visibly deforming. The fault is not visibly loading. By every direct surface measurement we have, the system is sitting still. If you take that data at face value, you would conclude that the new Madrid Seismic Zone is not currently storing significant new stress. You would conclude that whatever stress released in 1811 and 1812 may have been the accumulated stress of thousands of years, and that the system is now in a quiet phase. You would conclude that the hazard is much lower than historical estimates suggest. But there is a problem with that interpretation, and the problem is this. Surface geodesy, meaning GPS-based strain measurement, is only reliable for faults where the stress accumulation is concentrated in the upper crust, near the surface. On the new Madrid Seismic Zone, the seismic activity is occurring at depths of 5 to 15 miles. The fault systems are buried. The locked sections, if they exist, are deep. And stress accumulating deep in the crust does not necessarily translate into detectable surface deformation. The rock above the locked zone can absorb, distribute and mask the strain, so that by the time it reaches the surface, it is below the detection threshold of our instruments. In other words, absence of signal is not necessarily absence of stress. The fault could be loading invisibly, deep in the crust, in ways that our surface-based monitoring simply cannot see, and we would not know until the system released. This is what I call invisible loading. The idea that a fault can be quietly, progressively accumulating strain in a way that is undetectable with current surface monitoring technology. And the moment you accept that invisible loading is possible, the GPS data stops being reassuring. The GPS data becomes instead ambiguous. It is consistent with a dying fault. It is also consistent with a deeply locked fault that is loading invisibly. Both interpretations fit the data equally well. The measurements cannot distinguish between them. This is where the science becomes genuinely uncomfortable. Because the people who want to tell you that the new Madrid is not a real threat will point to the GPS data. And they are not wrong to do so. It is real data. It is high-quality data. It is the most direct measurement we have. But the people who want to tell you that the new Madrid remains a high-risk zone will point out that the GPS data has known limitations, that intraplate fault loading is poorly understood, and that the historical record shows this system has produced massive events before and could do so again. They are not wrong either. The new Madrid Seismic Zone is a system whose internal state cannot be directly observed. We can see when it releases. We cannot see what it is storing. We are forced, in effect, to infer the interior from the exterior, and the exterior is mostly silent. Today's magnitude 4 is a tiny piece of exterior. It is one data point, in a system that releases data points at a glacial rate compared to the questions we want to ask. It does not prove that the fault is loading. It does not prove that the fault is dying. It simply says once more that the fault is not dead. And that brings us to the scientists themselves, because the divide we have just described between the dying fault interpretation and the loading fault interpretation is not a hypothetical debate. It has names attached to it. It has published papers. It has decades of professional disagreement behind it. And today's earthquake just threw another rock into the middle of that argument. Part 7. The Dying Fault Hypothesis. To properly understand the state of the science around the new Madrid Seismic Zone, you have to understand that there is a very specific, very serious, very well-credentialed argument that says this fault is, essentially, winding down. That the hazard estimates we have been using are overstated. That the 1811 and 1812 sequence may have been a final release event, or at least a major release event after which the system will be quiet for a very long time, possibly permanently. This is not a fringe position. It is not a contrarian opinion offered by a single outlier. It is the published peer-reviewed work of some of the most respected seismologists in the United States, including researchers like Seth Stein at Northwestern University and Eric Calais, who has spent decades analysing the GPS data from this region. Their work has shaped a generation of thinking about intraplate seismic hazard, and their central argument is, in essence, that the new Madrid Seismic Zone does not show the kind of ongoing strain accumulation we would expect from a fault that is still actively loading. The argument goes something like this. Faults that produce large earthquakes do so because they accumulate stress over time. If the new Madrid Seismic Zone were actively loading toward another large event, we would expect to see measurable strain accumulating across the region. We have had GPS networks in place for decades now, with precision improving continuously. The measurements have not shown that strain. Year after year, the ground has not visibly deformed in ways that would indicate an actively loading fault. This is real, high-quality data collected over many years, and it is difficult to dismiss. From that observation, the dying fault hypothesis makes the following leap. If we are not seeing strain accumulate, then perhaps the system is not accumulating strain. Perhaps the 1811 to 1812 sequence released most of the stress that had built up over the previous thousands of years, and the system has since entered a quieter phase. Perhaps the recurrence interval for large events in this zone is much longer than some traditional estimates suggest. Perhaps the hazard, as currently modelled, is overestimated. The implication of this view, if it is correct, is significant. It would mean that the probabilistic seismic hazard maps for the central United States overstate the risk. It would mean that the massive investments in seismic retrofitting and earthquake preparedness in states like Missouri, Tennessee, Arkansas, and Illinois, while not wasted, may be solving for a less urgent problem than the public has been led to believe. It would mean that the next 1811 event is, statistically, much further away than the hazard maps suggest. This is a scientifically serious position. It is grounded in real data. It is argued carefully, and it has been published in major journals, and it has generated decades of productive debate. But it has weaknesses. The most obvious weakness is that the fault, despite the supposed quiet, continues to produce small earthquakes. Every year, roughly 200 small events are catalogued inside the zone. Every few years, events in the 3 and 4 magnitude range occur. Today's magnitude 4 is a fresh reminder of that. If the fault is truly dying, it is not yet dead. Something is still moving down there, something is still releasing energy. That is not conclusive evidence against the dying fault hypothesis, because small quakes can occur as residual activity long after a fault has passed its main life cycle. But it does mean that the system is not fully quiet, and it means that every small event becomes, in some small way, a test of the hypothesis. The second, and arguably more important weakness is the one we discussed in the previous section. Surface geodesy is limited in its ability to detect strain that is accumulating at mid-crustal depths. If the fault is loading invisibly, deep in the crust, the GPS data will not show it until the system is close to failure. So the absence of surface strain, which is the strongest piece of evidence for the dying fault hypothesis, is not as definitive as it might first appear. It is consistent with the hypothesis, but it does not prove it. There is also the simple scientific humility of acknowledging that we cannot directly observe the deep loading state of any fault system. We infer it from surface measurements, we infer it from historical records, we infer it from geological evidence, and every inference carries uncertainty. The dying fault hypothesis is one reasonable inference. It is not the only reasonable inference. Today's magnitude 4 is, in that sense, a stress test of the dying fault model, not a refutation, not a validation, a stress test. It does not prove the model wrong, because a single magnitude 4 event is well within what even a dying fault could produce as residual activity. But it does, once again, force the people who hold this view to explain why a supposedly decaying system continues to generate events that break multi-year silences and are felt across 5 states. And this is where the counter-argument comes in, because while the dying fault hypothesis is built primarily on modern instrumental data, there is another body of evidence that looks much deeper into the past, and it tells a very different story. Part 8. The paleoseismic counterargument. If you want to know whether a fault has produced large earthquakes in the past, you cannot rely only on the historical record. The historical record for most of the United States only goes back a few hundred years. For the eastern part of the country, detailed records start showing up somewhere around the late 1700s. That is not enough time to capture the natural cycle of a fault that might only produce major events every several hundred to 1,000 years. To see further back, you have to read the Earth itself. You have to look at the geological record. This is the field of paleoseismology, which is in essence the forensic analysis of past earthquakes through the physical evidence they leave behind in the ground. On the new Madrid Seismic Zone, the main pieces of paleoseismic evidence come from the sand blows I mentioned earlier. Remember, during the 1811 and 1812 sequence, violent shaking pressurized water-saturated sediments in the subsurface, forcing sand and water upward through the overlying soil, erupting at the surface in vents and fountains. Those eruptions leave distinctive deposits. They leave dikes of sand where there should be clay. They leave layered structures in the soil that record the moment of violent upward injection. And those deposits, once emplaced, can be preserved for thousands of years if they are buried and left undisturbed. Paleoseismologists have been digging trenches across the new Madrid zone for decades. They have been examining the soil layers in those trenches, identifying the sand blows, and dating the surrounding material using radiocarbon techniques on organic matter trapped in the sediment. And what they have found, repeatedly, is that the 1811 to 1812 sand blows are not the only ones in the record. There are earlier ones. There are much earlier ones. There are layers that record past sequences of large earthquakes, going back thousands of years. The specific numbers vary depending on which researcher you ask and which trench they are describing, but the general picture is this. The geological record suggests that the new Madrid Seismic Zone has produced multiple large earthquake sequences over roughly the last 4,500 years. The estimated recurrence interval between major sequences falls, in most studies, somewhere in the range of 500 to 1,000 years. That is an estimate with significant uncertainty, but it is derived from real physical evidence in the ground, not from modelling. If that recurrence interval is correct, and if we are currently about 214 years past the 1811 to 1812 sequence, then we are still in the early part of the cycle, but we are not at the beginning, and in some interpretations of the paleoseismic record, we may already be in the range where the next large event is plausible, even if not imminent. This picture directly contradicts the dying fault hypothesis. If the fault has produced multiple large sequences over the last 4,500 years, with reasonably consistent timing, then the idea that 1811 was a final release event becomes difficult to defend. The fault appears from the geological record to cycle, to release, to reload, to release again, to reload again. And if that pattern continues, then 1811 was not the end. It was one event in a sequence of events that, if history is any guide, has more installments coming. The geological record, however, is not without its own weaknesses. Dating ancient sand blows is not like reading a calendar. Radiocarbon dating has inherent uncertainty, often measured in decades or centuries for events this old. Not all sand blows are preserved equally well. Some may have been eroded away by floods, by river migration, by human land use. Some may be miscounted. Some may not be from the new Madrid zone at all, but from other sources of ground disturbance. There is a real preservation bias in the geological record, where more recent events are better represented than older events, and this can distort recurrence estimates. There is also a mismatch between geological timescales and instrumental timescales that makes reconciling the two datasets genuinely difficult. The geological record sees events over thousands of years, with uncertainty of decades to centuries on timing. The instrumental record sees events over decades, with precision of seconds on timing. Trying to fit these two views of the same fault into a single coherent picture is extremely hard. They are not observing the same thing at the same resolution. So where does that leave us? We have two bodies of evidence that tell us different things. The instrumental and GPS data suggest a fault that may be winding down. The paleoseismic data suggests a fault that cycles. Both interpretations are defensible. Both are held by serious credentialed researchers. And both are consistent with the possibility that large earthquakes could occur again on this fault, because even the dying fault hypothesis allows for the possibility of residual large events, and the cycling hypothesis obviously expects them. In other words, both models still allow, in some form, for the possibility that the next large New Madrid event is ahead of us, not behind us. The disagreement is about how likely, how soon, and how massive. It is not about whether it could happen at all. And into that unresolved debate, today's magnitude 4 arrives as a small, cryptic piece of new data. Not large enough to change the debate, not small enough to be ignored, a fresh data point that both sides can interpret to their advantage, and neither side can conclusively claim. Part 9. Where the April 23rd Quake fits. So where exactly does this morning's magnitude 4 event sit in this tangled scientific argument? Let me say it as plainly as I can. It does not resolve the debate. It does not decide the question. It is too small to shift the hazard models in any meaningful way, and it is too large to dismiss as random background noise without hesitation. It sits in that uncomfortable middle space that Earth science is full of, events that are real, measurable, and statistically ordinary in isolation, but psychologically and contextually disruptive when you zoom out and look at timing, location, and recent history together. It is a data point in motion, not a conclusion. What it does, however, is break the recent narrative of silence. For the people who have been pointing to the relatively quiet behaviour of the last few years in the new Madrid Seismic Zone as evidence that the dying fault interpretation might be correct, today's event is an inconvenient observation, not a fatal contradiction, not a collapse of the hypothesis, but something that forces a pause in how cleanly that story can be told. Because whatever interpretation you prefer, whether you believe the system is gradually stabilising or still actively loading stress deep in the crust, you now have to account for the fact that it just produced a widely felt magnitude 4.0 earthquake after a relatively quiet month. That fact does not go away. It has to be absorbed into the model. For the scientists who take the opposite view, that the new Madrid system remains a legitimate seismic hazard capable of producing damaging earthquakes on long but real recurrence intervals, today functions as modest reinforcement. Not confirmation in the dramatic sense, not vindication, and certainly not a signal that anything larger is imminent. Seismologists are extremely careful about this point for good reason. Small to moderate earthquakes are common in many systems that never produce large ones immediately afterward. But the event still matters in a softer way. It keeps the system active in the catalogue. It reminds everyone that quiet does not mean inactive. And it provides one more example that can be compared against long-term statistical behaviour. In that sense, a magnitude 4 is not about prediction. It is about continuity. It tells you that the fault is still participating in the slow, uneven process of stress release and accumulation that defines tectonic systems. It does not tell you what comes next, and anyone who tries to extract that level of certainty from a single event is stepping outside what the data can support. But even if the scientific meaning is limited, the interpretive meaning is not. Because the most honest framing of today's earthquake is that it reopens a conversation that had been gradually fading from public attention. In the absence of large or even moderate seismic activity, public and institutional focus naturally drifts. Monitoring continues, of course, through agencies like the Federal Emergency Management Agency and regional seismic networks, but attention is not the same as instrumentation. Funding priorities move toward more immediate risks. Public awareness declines. Emergency preparedness in regions like the central United States becomes something that exists in documents and scenarios, rather than in active conversation. Today interrupts that drift. Not because the earthquake is large enough to be dangerous in itself, but because it reintroduces the system into awareness. It forces the mental map of the region to update. It reminds anyone paying attention that beneath the Mississippi River Valley lies not a static foundation, but a complex and still active tectonic feature with a long and violent history. And that history is not abstract. This is the same system responsible for the 1811 to 1812 New Madrid earthquakes, a sequence of earthquakes so powerful that they reportedly rang church bells as far away as the East Coast, temporarily altered the course of the Mississippi River, and produced ground deformation severe enough to create new lakes and permanently reshape parts of the landscape. Those events did not occur in a modern infrastructure environment, which is an important distinction, but they do provide a reference point for what this fault system is capable of under extreme conditions. So when a modern magnitude 4.0 occurs, it does not tell you that another 1811 is coming, but it does force you to remember that the physical system beneath the ground has already demonstrated the capacity for events far beyond anything experienced in recorded US history in that region. That is why today is less about hazard and more about attention. It is a reminder event, a reactivation of curiosity, a small signal that says the system is still part of the present tense, not just the historical record. And this is where the interpretation becomes more nuanced than the headlines or initial reactions tend to allow. Because it is true that this event does not significantly change the probability models used by geologists. It is also true that it does not strengthen the argument that a large earthquake is imminent, but it's equally true that it reintroduces uncertainty into conversations that had become quieter in recent years. It is a reason to keep the question alive rather than close it. Is the fault dormant in a meaningful geological sense, or is it simply quiet on human timescales, while continuing to accumulate or redistribute stress at depth in ways we cannot directly observe? That is still the core question, and today's earthquake does not answer it. It only confirms that the question is still valid. One of the most important things to understand here is that science does not fail because it lacks certainty in cases like this. It is actually functioning exactly as intended. When dealing with systems like deep crustal fault zones, scientists are working with incomplete observability. They cannot directly measure stress at depth across the entire fault plane. They cannot watch rupture nucleation in real time at the scale and resolution needed to predict individual events. Instead, they rely on indirect signals, surface deformation, seismic catalogues, historical reconstruction, and probabilistic modelling. That means uncertainty is not a temporary gap waiting to be filled. It is a permanent feature of the system. What changes over time is not the existence of uncertainty, but the structure of it. Some models become more constrained. Some hypotheses become less likely. Others remain viable for decades. And occasionally, a small event like today's shifts the weight slightly. Not enough to change conclusions, but enough to keep multiple interpretations alive. That is exactly where we are now. The dying fault hypothesis, associated in part with researchers such as Seth Stein and Eric Calais, remains a serious scientific position supported by certain geodetic measurements suggesting minimal strain accumulation across the region. The alternative view, grounded in paleoseismic evidence from sedimentary records and liquefaction features, argues that large earthquakes in this system recur on timescales of hundreds to thousands of years, implying that the system is still capable of major future events. Both interpretations are built on legitimate data. Both have limitations, and neither is conclusively disproven by a magnitude 4.0 earthquake. What today's event does is keep that tension active. It ensures that the new Madrid Seismic Zone does not fade into the background of solved problems in the public imagination. It ensures that when emergency planners revisit risk scenarios, they are not doing so in the absence of recent activity. And it ensures that the scientific conversation remains anchored to real, recent observations rather than purely historical reconstruction. But while all of that is happening in the background of scientific interpretation, there is another layer of this story that has to be addressed carefully because it shapes how people perceive events like this in real time. Context collapse. Today's earthquake did not occur in isolation. It happened on a day when the sun produced major flares from an active sunspot region, launching a coronal mass ejection that is now travelling through space. It happened during a period when multiple seismic zones around the world were also active, including a swarm near Crete. And even though none of these systems are physically connected in a direct causal way, the human brain does not naturally separate unrelated systems when they appear to synchronize in time. That is why these moments feel significant even when the underlying physics does not support a connection. The sun is not driving the earthquake. The earthquake is not influencing the sun. And the Mediterranean seismic activity is not linked to either in any physical mechanism that current science supports. What is happening instead is that independent systems are producing activity simultaneously, and our perception is stitching them into a single narrative because that is how pattern recognition works under uncertainty. This is not a flaw in thinking, it is a feature of cognition. But it does mean we have to be careful about interpretation, because the real story is not that everything is connected. The real story is that multiple complex systems are always active at once, and occasionally their outputs overlap in time in ways that feel meaningful, even when they are not physically linked. So when we step back from the noise of simultaneity and focus only on the New Madrid event itself, the picture becomes clearer and more grounded. A moderate earthquake occurred in a historically significant fault system. It was widely felt but not damaging. It followed a short period of relative quiet. It sits within the expected range of seismic behaviour for the region, but at the upper end of recent local activity. It does not indicate an imminent large earthquake. It does not invalidate existing hazard models. It does not resolve long-standing scientific disagreement. What it does is remind us that the system is active, that it is still producing energy releases, and that our understanding of its deeper behaviour remains incomplete. And that brings us back to the most important point in all of this. Uncertainty is not something we eliminate in Earth science at this level. It is something we manage. We build probabilistic models. We monitor continuously. We refine interpretations as new data arrives. And we accept that for certain systems, especially those buried deep in the crust and operating on long time scales, there will always be a gap between what we can measure and what is actually happening. The new Madrid Seismic Zone sits squarely inside that gap. Today's magnitude 4.0 earthquake does not close it. It does not widen it dramatically either. It simply marks another moment in its long existence where the system revealed itself just enough to remind us it is still there. And in a way, that is the most important takeaway. Not that something big is coming, not that something is safe, but that the system is still active, still complex, still partially hidden, and still behaving in ways that require us to pay attention over long periods of time rather than short bursts of news cycles. So we return to the question we started with. Where does today's event sit in the scientific argument? Right in the middle, not as an answer, not as a prediction, but as a reminder that the argument is still ongoing, the system is still active, and the Earth is still doing exactly what it has always done, moving quietly most of the time, and occasionally in ways that briefly force us to look more closely at what we thought we understood. Part 10. The Crete Swarm Contrast. On the same day that the new Madrid Seismic Zone produced its magnitude 4 event, roughly 6,500 miles away, in the eastern Mediterranean, off the southern coast of the Greek island of Crete, an earthquake swarm broke out. The largest event in that swarm was a magnitude 5.8. Multiple smaller events, some in the 4 and 5 range, followed within hours. It was a classic swarm signature. Clustered events, similar magnitudes, no single dominant main shock, all within a tight geographic area. For a viewer looking at a global earthquake map on the day we're discussing, the simultaneous activity of a magnitude 4 in Tennessee and a magnitude 5.8 off the coast of Crete might look, at first glance, like a planet in motion. 2 earthquakes, half a world apart, on the same day. If you're inclined to see systems talking to each other, this is exactly the kind of image that feeds that inclination. But the geological setting of the Crete event could not be more different from the new Madrid event. And understanding that difference is, I think, the most useful thing we can do with this comparison, because it illustrates exactly why we should not be drawing lines between these 2 events. Crete sits at the southern edge of the Aegean region, in one of the most tectonically active zones in the world. To the south of Crete, the African plate is slowly subducting, meaning sliding underneath the Aegean Sea plate, which is a smaller fragment of the Eurasian plate. This is a subduction zone, one of the most classic settings for large earthquakes on the planet. Subduction zones are where the biggest earthquakes in the world happen. The 2011 Tohoku earthquake in Japan, the 2004 Sumatra earthquake, the 1960 Valdivia earthquake in Chile, all were subduction zone events. Not all subduction zones produce mega earthquakes all the time, but they are all capable of significant seismic activity, and they all produce earthquake swarms, moderate quakes, and occasionally catastrophic events. A magnitude 5.8 near Crete is, in the context of its tectonic setting, not surprising. It is not anomalous. It is not a broken pattern. It is essentially the subduction zone doing what subduction zones do. Swarms happen there. Moderate quakes happen there. Even large quakes occasionally happen there. It is a zone that is expected to be active, and when it is active, no one has to reach for an unusual explanation. The tectonic setting explains it fully. History backs this up. The Crete region has produced massive seismic events in the past. In 365 of the Common Era, a huge earthquake, probably a magnitude 8 or larger, struck the region and generated a tsunami that devastated coastal cities across the eastern Mediterranean, including Alexandria in Egypt. That event is one of the most well-documented ancient megathrust earthquakes in historical record. and it reminds us that the Hellenic subduction zone, which runs south of Crete, is capable of producing genuinely catastrophic events. A magnitude 5.8 today is orders of magnitude smaller than that, but it sits in a part of the world where the crust is constantly actively moving, where seismicity is the rule rather than the exception, and where moderate events are part of the normal rhythm. Compare that to the New Madrid Seismic Zone, an intraplate system deep inside a stable continental plate, 1,000 miles from the nearest plate boundary. A system where the surface is not visibly deforming. A system where earthquakes, especially significant ones, are not expected and are not easily explained by reference to the regional tectonic setting. A magnitude 4 in the New Madrid zone is in many ways a more anomalous event than a magnitude 5.8 near Crete, even though the Crete event is actually larger. This is because we expect Crete to rumble. We do not expect the Mississippi Valley to rumble. So what the comparison tells us is not that the two events are connected. It is that Earth has multiple seismic regimes operating simultaneously at all times, and that clustering them in time, on any given day, is going to produce the illusion of synchronization even when no synchronization exists. The planet does not pause one subduction zone while another intraplate fault releases stress. Both are active, both are producing events, both show up on the daily seismic map, and when they both produce something notable on the same day, our brains assemble that into a story, but the physics does not. This is the reinforcement I want to offer. The Crete event does not mean the New Madrid event was part of some larger global phenomenon. The Crete event means the Hellenic subduction zone was doing what subduction zones do. The New Madrid event was doing what the New Madrid does, whatever that actually is, and the fact that they happened on the same day is a temporal coincidence, not a physical linkage. The fault that reversed the Mississippi does not need Crete's permission to produce a magnitude 4, and Crete does not need to check in with the New Madrid before producing a swarm. They are independent systems. They look connected only because we are watching both of them at once. But there is a second layer of global context to address, and this one touches on an entirely different regime of physics altogether. This one takes us off the planet. And this is the one where the temptation to see connections is actually the strongest, because the correlations have been studied, the hypotheses have been proposed, and the science is genuinely unresolved. Part 11. Solar activity. What actually matters. Let's talk about the Sun. On the same day as the New Madrid earthquake, the Sun was active. Specifically, a sunspot region catalogued as active region, 4419, produced 2 X-class solar flares within a 7-hour window. X-class is the highest category of solar flare on the standard classification system, representing the largest, most energetic type of flare the Sun produces. The flares also launched coronal mass ejections, and at least one of those ejections, based on early trajectory modelling, is Earth-directed. The coronal mass ejection, or CME, is still in transit as we speak. It has not yet reached Earth. It is expected to arrive in a window of roughly 1 to 3 days after launch, depending on its speed and the intervening solar wind conditions. So the Sun is active, the Sun launched a large energetic event toward us, and in the public conversation around earthquakes, there is a persistent idea that solar activity and seismic activity are linked, that the Sun can, in some way, trigger earthquakes, that geomagnetic storms driven by coronal mass ejections can stress the Earth's crust and cause or amplify seismic events. I want to address this carefully because the idea is not entirely without scientific foundation, but it is widely overstated in popular discussion, and the timing of today's events breaks the simplest version of the causal story. First, the timing. The most important fact is that the New Madrid earthquake happened before the solar flares reached their peak, and certainly before any coronal mass ejection impacted Earth. The quake came first. The flares occurred later in the same calendar day, and the CME will not arrive for another day or more. Any theory that says the Sun caused this earthquake has to explain how an effect arrived before its cause. That is not how physics works. The timeline alone rules out any direct causal link between today's solar activity and today's quake. Could today's solar activity somehow affect Earth seismicity in the next few days, after the CME arrives? This is where the scientific honesty gets more interesting. There is a body of research, some of it from Japan and Europe, that has looked at statistical correlations between geomagnetic activity and earthquake occurrence. Some of that research has found weak statistical associations, One specific hypothesis, sometimes referred to as capacitive coupling, proposes that strong geomagnetic disturbances induce electrical currents in the Earth's crust that could, in very specific geological settings, influence the stress state of certain faults and slightly alter the timing of earthquakes that were already close to happening. This hypothesis is genuinely interesting. It is also genuinely limited. The proposed effect, if it exists, is extremely small. It would not cause earthquakes. It would at most slightly modulate the timing of earthquakes that are already close to triggering. The statistical associations found in the literature are weak, often not reproducible across different datasets, and have not produced any reliable predictive model. The mainstream consensus in seismology is that space weather is not a meaningful driver of earthquake occurrence. Some researchers disagree and their work is worth reading, but it has not changed the overall picture. So what should you take away from the sun's activity today? A few things. First, today's flares did not cause today's earthquake. The timeline forbids it. Second, the coronal mass ejection currently en route to Earth may or may not cause geomagnetic effects over the next few days. If it does, those effects are going to matter much more for power grids, satellite operations, GPS accuracy, and high-frequency radio communications than for earthquake activity. The primary impacts of a coronal mass ejection are in the magnetosphere and the upper atmosphere, not in the crust. Third, the persistent popular narrative that solar activity drives major earthquakes is not well supported by current science. There may be small, specific, subtle effects in edge cases. There is not a reliable connection that would allow anyone to predict quakes from flares or to explain today's New Madrid event by reference to today's flares. The solar convergence, in other words, adds atmospheric tension to the story of today, but it does not add explanation. It makes today feel more eventful. It does not make the New Madrid earthquake more predictable, more understandable, or more concerning than it would be in isolation. The sun is not telling us what the fault means. The sun is doing its own thing, on its own schedule, and the fact that we are watching both today is, again, temporal coincidence rather than physical coupling. And this pattern of apparent coupling, where multiple unrelated systems produce elevated activity in the same window of time, is not unique to today. It happens constantly, across all timescales, and it has a specific effect on human perception that is worth naming directly, because it shapes how we interpret events like the one we saw this morning. Part 12. The Planet in Motion Illusion. Zoom out with me for a moment. Set aside the New Madrid, set aside Crete, set aside the solar flares, and look at the global seismic map over a random 24-hour window. Any random window, not today, not a famous day, just a normal Tuesday from last year. Pick one at random. On that random Tuesday you will find, without fail, somewhere between 50 and 100 earthquakes around the world. Most of them will be small, below magnitude 4. A handful will be in the 4 to 5 range. 1 or 2 will be in the 5 to 6 range. Occasionally a magnitude 6 or 7 will show up somewhere, maybe in Indonesia, maybe in the Pacific Northwest, maybe off the coast of Tonga. This is the baseline of global seismicity. It is continuous, it never stops. The Earth is always releasing stress somewhere through some fault, every single day. And within any random 24-hour window, if you also look at solar activity, you will find that the sun is often producing flares of various classes. Sometimes geomagnetic storms are already underway. Sometimes coronal mass ejections are in transit. The sun is also always doing something. The quiet days are the unusual ones. What this means is that, on any given day, you can find a seismic event somewhere in the world, a solar event somewhere in the sun's atmosphere, and a local weather anomaly somewhere on Earth, and string them together into what looks like a pattern. The pattern is constructed entirely by your choice of window and your choice of events to highlight. The underlying reality is that all of these systems are active, all of the time, and clusters are not exceptional. They are the norm. This is what I mean by the planet in motion illusion. The perception that when multiple unrelated systems produce notable events in the same temporal window, the planet itself is entering some special state of elevated activity. In almost all cases, that perception is wrong. The events are independent. The clustering is statistical, not physical. Human cognition constructs the narrative of system-wide synchronization because human cognition is evolved to find patterns. and it is particularly good at finding patterns where none exist. On the day we are discussing, the Alaska region was seismically active. The Kamchatka Peninsula, in Russia's Far East, produced moderate seismic events. The Aleutian Islands produced some activity. These are all parts of the Pacific Ring of Fire, one of the most tectonically active regions on the planet, and they are almost always producing events at some level. Pointing to them as evidence that today was a special day of global seismicity is like pointing to cars on a highway as evidence that something unusual is happening in traffic. They are always there. Their presence is not the news. I'm not saying that the convergence of events today is meaningless. I'm saying that the meaning is about perception, not about physics. The convergence makes the New Madrid event feel contextually louder than it would on a quiet day. If the sun were calm and Crete were quiet and Alaska were boring, a magnitude 4 in Tennessee would still have happened, still have been felt across 5 states, still have been worth reporting. The quake itself would not be different, but it would read differently in the minds of the people watching because it would stand alone rather than appearing as one voice in a chorus. What we need to do is separate those two things carefully. The event itself is what it is. A magnitude 4 inside the core of the New Madrid Seismic Zone after a month of near silence on a fault that once reversed the Mississippi. That story is the story, and it stands whether or not anything else is happening on Earth or in space. The convergence is noise. The convergence is coincidence. The convergence is interesting but not informative. This is the discipline of holding the central thread. The central thread of tonight's story is the New Madrid fault, its behaviour, its debate, and its meaning. Not the sun, not Crete, not Kamchatka. Those are context, and context is useful, but only if it does not displace the main question, and the main question remains exactly what it was at the beginning of this video. Is the fault truly dormant, or is it quietly reloading? And did today's small event give us any information at all about which of those is true? And now, we have to turn to the part of the story that actually matters for the people who live on top of this fault. Because whatever the answer turns out to be, the consequences of getting it wrong are not abstract. They are measured in bridges and pipelines, and hospitals, and people. And this is where the real weight of the conversation comes to rest. Part 13. What a real New Madrid event would mean. Let's leave the abstract scientific debate for a minute, and talk about what would actually happen if the New Madrid Seismic Zone produced another 1811 class sequence in the modern era. Not a magnitude 4, a magnitude 7.5, or a repeat of the 3-event sequence from 1811 and 1812 spread over several weeks. I want you to hold that image in your head for a moment, because it is the image that every serious emergency planner in the central United States has to live with, even if the rest of us never think about it. This scenario has been modelled extensively by the Federal Emergency Management Agency and by regional emergency planning organisations. The results are, in the polite language these organisations tend to use, sobering. In the less polite language I can use, they describe what is probably the largest potential inland disaster in the continental United States that is not a hurricane or a pandemic. And unlike a hurricane, it would arrive with essentially no warning. No 5-day forecast cone, no evacuation window, no chance to board up windows, fill the bathtub, or drive inland. One moment, it is Tuesday afternoon in Memphis. The next, the ground is moving in a way that most people in the region have never experienced, do not recognise, and have no muscle memory for. The first 30 seconds would tell the story. The next 30 years would tell the aftermath. The immediate impact zone of a magnitude 7.5 on the New Madrid would include Memphis, Tennessee, with a metropolitan population of over 1 million. It would include St. Louis, Missouri, with another 2.5 million. It would include Little Rock, Arkansas, parts of southern Illinois, western Kentucky, and significant portions of northern Mississippi. The shaking intensity in the immediate epicentral region would be extreme, strong enough to cause partial or total collapse of many older structures, especially unreinforced masonry buildings, which are disproportionately common across this region compared to the modern building stock of California. Think brick schools from the 1920s. Think courthouse squares that have stood since before the Civil War. Think warehouses along the river, 4 and 5 stories of unreinforced masonry, sitting directly above soft, water-saturated soil that amplifies ground motion the way a subwoofer amplifies bass. The buildings were never designed for this. Many of them were designed before seismic codes existed anywhere in the United States. But the truly alarming part of the modelling is not just the direct shaking damage, it is the infrastructure cascade. The Mississippi River corridor is one of the most important logistical arteries in the United States. It carries a significant fraction of the nation's agricultural exports, a significant fraction of its bulk commodities, its fuel, its industrial materials. Thousands of miles of pipelines run through the region, carrying natural gas, petroleum and refined fuels to the rest of the country. The electrical grid that serves the central and eastern United States passes through, and in many cases is anchored in the zones that would be most affected. Every loaf of bread on a supermarket shelf in Atlanta, every gallon of gasoline at a station in Ohio, every industrial part moving through a factory in Pennsylvania, traces some fraction of its journey through this corridor. The country is stitched together in ways most of us never consciously notice, by the lines that cross this fault. A large New Madrid event would, according to FEMA modelling, rupture pipelines, collapse bridges across the Mississippi and its tributaries, damage rail infrastructure, disrupt electrical transmission lines, and potentially trigger failures at industrial facilities across the region. The Mississippi River itself could be rendered temporarily unnavigable due to riverbed deformation, bridge debris, and damaged locks. Rail corridors running east to west across the central United States could be severed at multiple points. Major highways, including interstate arteries, would be compromised where they cross bridges in the affected zone. Interstate 55, Interstate 40, Interstate 24. The major crossings are concentrated exactly where the fault would do the most damage. In the hours after the event, the map of the United States would functionally split in two, not politically, not culturally, but logistically. Moving freight from the eastern half of the country to the western half would become extraordinarily difficult overnight, and in some corridors temporarily impossible. The consequences would not stay local. The economic and logistical impact would ripple across the entire continent. Fuel shortages could propagate through the eastern United States within days. Agricultural shipments from the Midwest to export terminals could be halted for weeks or months. The electrical grid disruptions could trigger cascading failures across multiple interconnection zones. Financial markets, supply chains, and manufacturing operations that depend on central US logistics could be destabilized at a national scale. And I want to be specific here, because the phrase supply chain disruption has lost some of its weight in recent years. What we are talking about is not late shipments. What we are talking about is pharmacies in Cleveland running out of insulin because the distribution hub in Memphis went offline. Gas stations in North Carolina posting closed signs because the pipeline that feeds them ruptured at a river crossing. Factories in Michigan idling because the rail cars carrying their parts are stranded on the wrong side of a collapsed trestle. The modern economy is a choreography, and when you remove one of the dancers, the whole performance stumbles. This is not hypothetical fear-mongering. These are scenarios that federal and state emergency planners have wargamed for decades, with estimated economic losses in a full 1811 scale scenario running into the hundreds of billions of dollars, potentially exceeding $1 trillion depending on secondary effects and recovery timeframes. The human cost in terms of injuries, deaths, displacement and long-term disruption is harder to model, but it would be measured in numbers that would reshape the country's relationship with seismic risk for a generation. It would be the kind of event that divides American history into before and after, the kind of event your grandchildren would learn about in school, the way you learned about the 1906 San Francisco earthquake, or Hurricane Katrina, or the 9/11 attacks, a punctuation mark in the national story, drawn in the ink of a single afternoon. Compare that to the impacts of the 1811 and 1812 earthquakes themselves adjusted for modern conditions. In 1811, the region was sparsely populated. Indigenous communities, a handful of frontier settlements, no modern infrastructure. The physical effects of the earthquakes, massive as they were, caused relatively limited loss of life, because there was very little to be damaged. The landscape bore the scars in things like Reelfoot Lake, but the human toll was small by modern standards. The frontier absorbed the shaking the way an empty room absorbs a gunshot. Loud, yes. Terrifying, yes. But with nothing fragile in the way. Today, the same event would occur in a region with tens of millions of people living directly in the impact zone, millions more in the broader affected area, and critical national infrastructure overlaid across every square mile of it. The difference between 1811 and a hypothetical 2026 version of the same event is not the earthquake. It is what the earthquake would encounter, and what it would encounter is a modern industrial society that has, for the most part, assumed this would not happen. Every bridge, every pipeline, every hospital, every nursing home, every data centre, every school, every grocery distribution warehouse, built on the quiet collective assumption that the ground beneath them would remain the ground beneath them. The assumption holds almost always. The entire point of tonight's story is that almost always is not the same as always. Today's magnitude 4 is not that event. Let me be explicit about that again, because I do not want a single person watching this video to walk away thinking I am predicting a disaster. I am not. I cannot. Nobody can. Today was a small event, inside a system capable of national-scale disruption. It did not threaten any of the infrastructure I just described. It did not damage any buildings. It did not injure anyone. It barely registered as news outside the immediate region, and even inside the region, most people who felt it assumed a truck had hit their house, or the furnace had finally given out, or a neighbour was doing something unusually aggressive in their garage. But it is a reminder. It is a prompt. It is the system, such as we understand the system, murmuring that it exists. It is the fault clearing its throat in a room where almost nobody has been listening. And that reminder is more valuable than a lot of us realise, because as we're about to see, the preparedness posture of the region in question has drifted considerably from where, honestly, it should be. Part 14. The Preparedness Gap. If you live in California, earthquake preparedness is part of the cultural background. You know what a quake feels like. You have done drop cover and hold drills. Your building was probably constructed or retrofitted to at least some modern seismic standard. You have earthquake insurance, or at least you have thought about it. You have a go bag. You know where your water shutoff is. This is not universal, and preparedness varies, but it is present as a cultural baseline. The ground moves occasionally. Everybody knows it. Nobody panics about it. The knowledge sits in the back of the mind the way knowledge of winter sits in the back of a Minnesotan's mind. Of course it happens. Of course you prepare. It would be strange not to. If you live in Memphis, or St. Louis, or Little Rock, or Southern Illinois, the cultural baseline looks very different. Earthquake preparedness, in most of the New Madrid region, is not an active part of daily awareness. For many residents, the last significant earthquake in the region was more than 200 years ago, well before any living person's memory, well before modern infrastructure existed, well before anyone alive today has any direct personal frame of reference. The earthquakes are history, not lived experience, and history as a motivator for preparedness has a half-life measured in generations. Ask the average person in Memphis what a magnitude 7 would feel like, and you will get a shrug, a joke, or a confident wrong answer. Ask the average person in St. Louis where they would go if their house was no longer safe to be inside, and you will get silence. The information has not been transmitted across the generations because the event that would have transmitted it has not happened in any living memory. The cultural muscle has atrophied. This shows up concretely in several places. Earthquake insurance penetration across the central United States is estimated to be below 15% in most of the high-hazard counties. That is, less than 15% of homes and businesses in the most exposed areas carry earthquake-specific insurance coverage. Standard homeowner and property insurance policies almost universally exclude earthquake damage. A family home destroyed by shaking, in most cases, would not be covered by the standard policy. Let me say that again, because it is one of those facts that I think should be said out loud more often than it is. If a magnitude 7 struck Memphis tomorrow morning, the overwhelming majority of the homes destroyed would not be rebuilt by insurance. They would be rebuilt, if at all, by savings, by federal disaster assistance that takes years to arrive, by loans, by displacement, or simply not at all. Compare that to California, where earthquake insurance penetration, while still low, is significantly higher, and where the regulatory environment has made coverage somewhat more accessible. The gap is not explained by the science. The science says the central United States has real seismic risk. The gap is explained by the silence of the last 2 centuries. The building stock across the New Madrid region is also a problem. Unreinforced masonry buildings, brick structures built without the steel reinforcement and sheer walls that modern seismic codes require are disproportionately common in older neighborhoods across Memphis, St. Louis, and smaller cities throughout the region. These buildings, in a significant seismic event, tend to fail catastrophically. Walls collapse, roofs come down, occupants are trapped. The building type is, in earthquake engineering circles, sometimes called a killer building, and the central United States has a lot of them. They are beautiful in many cases. They are the historic fabric of downtown squares, of riverfront warehouse districts, of university campuses, of church neighborhoods. They are what gives these cities their character, and under strong enough shaking, they become the thing that defines the death toll. That is not a moral judgment, that is a structural engineering fact. Bricks without reinforcement do not bend, they come apart. And when they come apart at speed, they fall on whatever is underneath them. Modern building codes in the region do include seismic provisions, and new construction is generally built to a reasonable standard. But the existing building stock, much of it decades or more than a century old, does not meet those standards, and the cost of seismic retrofitting is high. Retrofits have been done in some cases, particularly for critical infrastructure like hospitals, fire stations and schools, but the coverage is incomplete. Private homes and commercial buildings, for the most part, have not been retrofitted. The vulnerability accumulates silently, year by year, as older buildings remain in use, and new construction adds only a thin layer of seismically reasonable structures on top of a much larger base of exposed stock. Imagine a city as a geological formation of its own. The modern buildings are the thin crust on top. The old buildings are the thick, brittle layer underneath. Most of the mass of the city, in seismic engineering terms, is the old layer. And the old layer is where most of the people live, work, shop, pray, and sleep. There are institutional emergency response plans for the region. The Central United States Earthquake Consortium exists. State emergency management agencies have new Madrid scenarios in their playbooks. There are federal coordination protocols. These are not nothing. I want to be fair to the people who have spent their careers on this problem because they have worked hard and they have made real progress, and they have done it largely without the public attention or funding that their West Coast counterparts have enjoyed. But they are not at the level of California's preparedness infrastructure, and they have not been tested by a real event in modern times. A plan that has never been executed is, at best, a theory. At worst, it is a comforting document that creates an illusion of readiness where none actually exists. The only way to know whether a plan works is to run it, and the new Madrid plans have not, in modern times, been run. The economic incentives around this vulnerability are, in a word, misaligned. Earthquake insurance is expensive and the event is rare, so most property owners choose not to purchase it. Retrofitting is expensive and the event is rare, so most property owners choose not to retrofit. Emergency preparedness programs are expensive and the event is rare, so most jurisdictions do not prioritize them at the level the risk models would suggest. Every individual choice is locally rational. The collective result is a region that is underprepared relative to the scale of the risk the scientists tell us exists. This is the tragedy of rare, high-consequence events. They do not reward the person who prepares for them, because in any given year the prepared person simply looks like the person who wasted money. Until, one year, they do not. Until, one year, they look like the only person who was paying attention, and by then, it is too late for everyone else. The disconnect between policy and reality is stark. The federal hazard maps place significant portions of the central United States in elevated seismic hazard categories. The probabilistic models for reasonable planning horizons suggest that there is a non-trivial probability of a significant event in the region over the next several decades. And yet the day-to-day preparedness, the insurance coverage, the building retrofits, the public awareness, all lag far behind what those probabilities would seem to demand. If you made a chart with the official hazard estimate on one axis and the practical preparedness level on the other, the central United States would sit in the corner of the chart that makes emergency planners wake up at 3 a.m. High risk, low readiness. It is the worst combination on the grid, and it has been the worst combination for decades. This is why every small signal from the fault matters, not because a magnitude 4 is going to damage anything. It is not. But because a magnitude 4 is a free, cheap, painless opportunity for the region to remember what it is sitting on. for the insurance agent in Memphis to get a few more calls next week, for the building inspector in St. Louis to have a slightly easier conversation with a property owner about retrofitting, for the emergency planner in Little Rock to get their next funding request approved, for the individual homeowner in Paducah to actually finally look up what a go bag should contain. A magnitude 4 does not hurt anyone. It is an advertisement, if you want to think of it that way, paid for by the Earth itself, for a kind of preparation that the region desperately needs and has mostly ignored. The advertisements do not come often. When they do, the smart move is to watch them. Small events are not the disaster. They are the rehearsal that the region largely has not been showing up to. And they do not come often enough. When one does happen, as today's did, the responsible thing to do is to treat it not as a prediction of something larger, but as a chance to close a tiny piece of the preparedness gap. Because whether or not the fault ever produces another 1811 event, the region will be safer if it behaves as though it might. That is not fear. That is not alarmism. That is just the cheapest, easiest, most rational response to the uncertainty that the science itself has told us lies beneath our feet. Part 15. The final question. So let me bring us back to where we started. Less than 24 hours ago, we published a video about a fault line buried beneath the middle of America that almost no one really talks about outside of geology circles. A system stretching under the Mississippi River Valley, locked into the deep crust, quiet enough that most people assume it is irrelevant in their lifetime. In that video, we laid out the history, the physics, and the uncomfortable uncertainty that sits at the heart of it. We talked about the fact that it produced one of the most extreme earthquake sequences in North American history in 1811 and 1812, and we talked about the modern debate that refuses to settle, whether that sequence was a once-in-geologic time release, or whether it was simply one cycle in a system that continues to load in ways we cannot directly observe. And we ended deliberately with an open question. What does it mean that something so large happened there before, and we still cannot confidently say what it is doing now? Today, that same fault moved. A magnitude 4.0 earthquake, upgraded from 3.9 after review. Not destructive, not catastrophic, not the kind of event that makes global headlines on its own. But it was felt across roughly 5 states, spreading through the central United States in a way that immediately reminded seismologists why this region is different from more familiar tectonic environments. It occurred inside the core of the new Madrid Seismic Zone north of Memphis, in the same structural system that once reshaped the Mississippi River itself, and it did not happen in isolation, at least not in terms of timing. On the same day, the Sun produced 2 X-class solar flares from active region 4419, launching a coronal mass ejection that is now moving through space toward Earth. On the same day, an earthquake swarm intensified near Crete, part of a broader burst of seismic activity in the Mediterranean region. And on the same day, smaller clusters of quakes were recorded in other parts of the world that are normally active but not always active at the same moment. We have spent time looking at all of this, not because we are trying to force a connection where one does not exist, but because when multiple systems that are usually studied separately appear active within the same narrow window of time, it is natural to ask whether we are seeing coincidence, or whether we are missing something about how these systems behave. Here is the most honest summary of what we can actually say without exaggeration, or speculation pretending to be certainty. The New Madrid earthquake today was real. It was the largest recorded event in that zone in roughly 5 years. It ended a short period, about 30 days, where seismic activity had been unusually quiet, with the largest event in that window only reaching magnitude 2.3. In terms of energy, the jump from those background levels to a magnitude 4.0 represents a change on the order of hundreds of times more energy released. That is not subtle in physical terms, even if it is not dangerous in practical terms. It was also felt widely because of the way seismic energy travels through this part of the continent. Unlike tectonic margins such as California, where fractured and complex crust tends to scatter and absorb seismic waves, the interior of North America behaves more like a solid acoustic medium. Energy travels farther, it remains coherent longer. That is why relatively moderate earthquakes in this region can be felt across states rather than counties. But even with all of that said, it is still a small earthquake in absolute terms. No damage, no injuries, no structural consequences reported, and importantly no immediate implication, based on anything seismologists currently understand, that this event signals an imminent larger rupture. It does not confirm that the new Madrid system is reloading toward another 1811 scale sequence. It does not invalidate the idea that the system may be in a long-term waning phase of activity. It does not resolve the fundamental disagreement in the scientific literature about whether strain is actively accumulating in a measurable way, or whether what we are seeing is residual adjustment in an old, mostly stabilized system. It is a single data point, and in seismology, single data points rarely change structural understanding on their own. But it is also not meaningless, because it interrupts something important, the expectation of continued quiet. It reminds us that the system is not dormant in the sense of being inactive. It is active at a low level, intermittently releasing stress, occasionally producing events large enough to be widely felt. It forces a re-engagement with a question that often fades into the background until something like this happens again. What kind of system is this actually, when we are not looking at it in long-term averages but in lived human timescales? The solar activity today is another layer of that same reality check, but it sits in a completely different physical domain. The Sun produced 2 X-class flares, among the most energetic categories of solar eruption, associated with a complex sunspot region. These flares are driving a coronal mass ejection that is expected to interact with Earth's magnetic field in the coming day or so. When that interaction happens, it will likely produce measurable space weather effects, disturbances in radio communication, increased radiation exposure for satellites, and possibly enhanced auroral activity at lower than usual latitudes. But it will not drive earthquakes on Earth in any established, reliable, or scientifically supported way. There are hypotheses in the scientific literature exploring weak or indirect coupling mechanisms between solar activity and geophysical systems, but none of them provide a mechanism that would allow a solar flare today to trigger an earthquake in a specific fault system on the same day. More importantly, the timing itself rules out any direct causal interpretation in this case. The earthquakes happened before the strongest solar emissions even left the Sun, so what remains is coincidence in timing, not causation in physics. The earthquake swarm near Crete is another piece of the same puzzle, but again, only in appearance, not in mechanism. The Mediterranean region is one of the most persistently active seismic zones on Earth due to the ongoing convergence between the African and Eurasian plates. Swarms and moderate earthquakes there are not unusual. What makes them feel connected in moments like this is not geology, it is simultaneity. We are seeing multiple datasets spike at once, and our brains are wired to interpret simultaneity as meaning. But tectonic systems do not synchronize across oceans on daily timescales. They do not share a common trigger in the way atmospheric systems sometimes do. They operate independently, driven by long-term plate motions and local stress conditions that evolve over years to millennia. So the global picture today is not evidence of a unified event. It is evidence of continuous background activity across multiple systems, some of which we are only noticing because our attention has been drawn to them at the same time. Which brings us back to the centre of all of this. We are left with a fault system that is old, deeply buried, and only partially observable. A system that once produced catastrophic earthquakes capable of reshaping rivers and being felt across an entire continent. A system that now produces mostly small to moderate events, but occasionally reminds us that it is still capable of releasing stored energy in ways that matter locally and regionally. We are left with a scientific community that does not agree on whether this system is still actively loading stress in a meaningful way, or whether it is gradually settling into long-term stability. Both interpretations exist in peer-reviewed literature. Both have supporting evidence. Neither fully resolves the contradictions in the observational record. We are left with a preparedness landscape that does not match worst-case scenarios that have been modelled for decades. The central United States contains critical infrastructure, transport corridors, energy pipelines, urban centres that would be significantly impacted by a repeat of a large historical sequence. And yet, public awareness and mitigation measures remain limited compared to regions with more frequent seismic activity. And we are left with the fundamental limitation that defines all of Earth science at depth. We cannot directly see what is happening several miles beneath our feet. We infer it, we model it, we measure what reaches the surface. But the actual processes, stress accumulation, fault friction, rupture nucleation, remain partially hidden, reconstructed after the fact rather than observed in real time. This is why events like today matter, even when they are small. Not because they predict something large is coming, but because they are part of the sparse signal we use to understand a system we cannot directly observe. Each event is a data point. Each cluster is a pattern candidate. Each silence is also data, even if it is harder to interpret. The central paradox of the new Madrid Seismic Zone remains unchanged after today's earthquake. A fault that appears quiet on human timescales may either be resting between rare large events, or quietly accumulating stress that will eventually be released in a way that exceeds anything in recorded history for this region. Today's magnitude 4.0 does not tell us which of those is true. It only confirms that the system is still active at some level, still capable of releasing energy, still part of the broader tectonic behaviour of the continent. And that is where the honest conclusion sits. Not in certainty, not in prediction, but in observation. A moderate earthquake occurred in a historically significant fault zone. It coincided in time with unrelated solar and global seismic activity. It does not change the established scientific models in any immediate way, but it adds another line to the long record that scientists will continue to analyse, compare and reinterpret as new data arrives over years and decades. And there is one more thing worth saying clearly before we close. The coronal mass ejection from today's solar activity is still on its way. When it arrives, it will produce measurable effects in near-Earth space. That part of the story is not speculative, it is physics. What it does not mean is that we should expect corresponding seismic responses on Earth. The two systems are linked only in the sense that they share a planet, not in the sense that they directly influence each other in the short term. Still, it is worth paying attention, because Earth science often becomes clearer in retrospect. Patterns that are invisible in real time sometimes become obvious only after enough data accumulates, and sometimes events that seem unrelated at first eventually find explanation in mechanisms we do not yet fully understand. That is not a prediction. It is a description of how science actually works at the edge of uncertainty. So we leave this in a place that is deliberately unfinished. A fault moved today. The sun erupted today. The planet showed activity in multiple places today. None of these events definitively explain each other. None of them point clearly to a larger conclusion. But together they form a snapshot of a dynamic system, one that is always in motion, always releasing energy somewhere, always doing things slightly beyond the limits of our immediate intuition. And underneath all of it is the question that does not go away, no matter how many times we observe these systems. How much are we actually seeing, and how much is still hidden beneath layers of time, rock, and distance that we can only infer indirectly? Today's answer is simple. Less than we would like, but more than nothing. And that is enough to keep watching. This has been Project Nightwatch. Until next time.